So, students, I was telling you about the net resting membrane potential that was around -70 millivolts. We can calculate this with the help of an equation which is known as the Nernst equation. Nernst equation tells us about the ratio of any specific ion combining with outside and inside the cell. The formula of the Nernst equation is as follows. Electromotive force, or EMF, is equal to positive or negative 61 divided by Z and multiplied by the log of concentration outside divided by a concentration inside the cell. This 61 is constant for all ions. Z is represented by the electrical charge on the ion. For example, if there is a potassium ion, the value of Z will be +1. It is also positive for the sodium ions as well. Now let us do some math here for our both major ions. Sodium ions outside the cell are 142 milliequivalents per liter. And sodium ions inside the cell are 14 milliequivalents per liter. Putting these values in the Nernst equation, Z will be +1. Sodium outside is 142 and inside is 14. The total sum of this equation will be around +61 millivolts. Now, if we do the same for the potassium ions. Potassium ions outside the cell are 4 milliequivalents per liter. And potassium ions inside the cell are 140 milliequivalents per liter. Putting these values in the Nernst equation as well. Z will be +1 as potassium has a +1 charge on it. Potassium outside is 4 and inside is 140. The sum of this equation will be around -94 millivolts. So, the electromotive force on sodium will be +61 millivolts, and on potassium will be -94 millivolts. Now, we know that the permeability of potassium is more than the sodium ion, as well as its movement is also more in the nerve cells. If we have to define a percentage, then 90% of potassium is permeable and only 10% of sodium is permeable to the leakage. So, if we keep this ratio in mind, then you can calculate the resting membrane potential. There will be -94 millivolts of potassium multiplied by 0.9 as in 90% of permeability. Then there will be 61 millivolts of sodium multiplied by 0.1 as in 10% of permeability. The sum of both these values will be around -70 millivolts. This is the resting membrane potential of a nerve fiber.
Wow! You have made that extremely easy.
And can we calculate all kinds of resting membrane potential with the Nernst equation?
I am afraid that is not the case, Jenny. Nernst equation is only limited to calculating single ions. If there are several ions moving in the cell membrane at the same time, we use another equation known as Goldman equation. We will discuss this in a separate video. Let us quickly talk about the establishment of resting membrane potential. Resting membrane potential is created with the movement of ions. This movement can occur with certain phenomenon. Remember that ions have certain behaviors. Firstly, they will attract the opposite charges more like if there is negativity on the inside, they will find ways to attract positive charges so that positivity inside increases. And this also occurs vice versa. Like if there are same charges, say two same position ions like sodium, they will be repelling each other in the same manner. This phenomenon is known as electrostatic forces of attraction.
Just like how people say, opposite attracts.
Good one, Alex. Now the next behavior is that the ions will move from higher concentration to the lower concentration. Does anyone know what is that phenomenon?
I know. We call it diffusion.
Yes, the phenomenon is known as diffusion. Now the movement of ions will be due to these two behaviors, which we can name as electrostatic forces and diffusion.
So, the resting membrane potential is created through these two things.
Yes, let me tell you how a normal resting membrane potential is created. The three major factors involved in normal creation for resting membrane potential are: first, there will be diffusion potential for potassium. Then there will be diffusion potential for sodium. And lastly, addition of sodium-potassium pump. Now, my dear students, I have laid the foundation of resting membrane potential for you, so can you now tell me the resting membrane potential in each factor?
Yes. In diffusion potential for potassium only, the overall charge will be minus 94 millivolts as calculated earlier.
And in the diffusion potential where sodium is involved, the overall charge will be 61 millivolts.
But we also said that potassium ions have higher permeability, so they will leak along with potassium ions as well. Jenny, then we should add 61 millivolts to minus 94 millivolts, and it will be the total for minus 86 millivolts. Teacher, you are right. Lastly, sodium-potassium pump. When 3 sodium moves outside and 2 potassium ions move inside, this sort of creates an electronegativity of around negative 4 millivolts. Now if we add up all the factors, what will be the final answer?
Minus 94 millivolts for potassium, plus 61 millivolts for sodium and minus 4 millivolts for sodium-potassium pump. The total sum would be minus 90 millivolts.
Yes, this is the average resting membrane potential for the cells, but typically resting membrane potential varies from minus 10 to minus 90 millivolts. You know the reason for it, right?
Yes, due to the involvement of various other ions in different cells. It could be calculated by the Goldman equation, which we will learn in the next video.
Looks like you have got the basic concept for resting membrane potential. Hope you'll do great in your exams.
I will also be joining your class for action potential.
You're always welcome.
From medical students to seasoned professionals, sqadia.com offers engaging and dynamic content for your educational journey.